I am Michio Kaku, a theoretical physicist, a professor of physics, and someone who has spent his entire life trying to understand how the universe truly works, not as we wish it to be, but as the laws of nature demand it to be. And for decades, I have studied space, time, matter, and the future of humanity. And during this time, one question keeps returning again and again in public discussions, in media, and in popular science fiction. And that question is simple yet profound. Can Mars become our second Earth? And today I want to address this question not as a dreamer, not as a science fiction writer, but as a physicist who must follow evidence wherever it leads, even when that evidence contradicts our hopes. Because science does not exist to comfort us. Science exists to tell us the truth. And the truth about Mars is far more complex, far more fascinating, and far more unforgiving than most people realize. Because Mars is often presented as humanity's backup planet, a place where we might escape if Earth becomes uninhabitable. Yet when we examine Mars through the lens of physics, biology, and planetary science, we discover that Mars is not a second Earth waiting for us, but a harsh, alien world that actively resists human life at every level. And to understand why, we must first understand why Earth is so extraordinarily rare. Because Earth is not simply a rock orbiting the Sun. Earth is a finely balanced system where atmosphere, magnetic field, gravity, chemistry, and biology have aligned in a way that allows complex life to exist. And Mars, despite its surface similarities, lacks most of these essential ingredients. And this is not a matter of technology alone, but of fundamental planetary physics. Because Mars is smaller than Earth, with only about 38% of Earth's gravity.
And this single fact already creates a cascade of problems that technology cannot easily solve, because gravity is not just a force that keeps us on the ground. Gravity shapes our bones, our muscles, our blood flow, and even the structure of our brains. And in low-gravity environments, the human body begins to deteriorate in ways that are predictable, measurable, and deeply concerning. And we already see this with astronauts who spend only a few months in orbit, returning with weakened bones, reduced muscle mass, vision problems, and altered immune responses. And Mars would subject humans to this low-gravity environment not for months, but for years, or even entire lifetimes. And the human body simply did not evolve for such conditions, and evolution cannot be rushed on demand. And gravity is only the beginning of Mars's challenges, because Mars also lacks a strong magnetic field. And this is a critical issue that many people overlook, because Earth's magnetic field acts as an invisible shield, deflecting deadly cosmic radiation and charged particles from the Sun, without which life on Earth would struggle to survive. And Mars, having lost most of its magnetic field billions of years ago, is exposed directly to this radiation, meaning that any human living on the surface of Mars would be constantly bombarded by high-energy particles that damage DNA, increase cancer risk, and degrade the nervous system over time. And no amount of optimism can change the fact that radiation is one of the most serious barriers to long-term human survival on Mars, because shielding against it requires massive amounts of material, deep underground habitats, or technologies that do not yet exist at scale. And even then, complete protection may not be possible. And then there is the atmosphere, or rather the lack of one. Because Mars's atmosphere is incredibly thin, composed mostly of carbon dioxide, with surface pressure less than 1% of Earth's, meaning that liquid water cannot exist on the surface for long. And without liquid water, life as we know it cannot thrive. And while Mars once had rivers, lakes, and perhaps even oceans, those days are long gone, and the planet today is cold, dry, and hostile,
with average temperatures far below freezing and dramatic temperature swings that would place enormous stress on any human structure or biological system. And some argue that we could simply build domes, sealed habitats, or underground cities. And while this is theoretically possible for small research outposts, it does not constitute a self-sustaining civilization, because a true civilization requires agriculture, open ecosystems, large populations, and long-term stability. And Mars offers none of these naturally, meaning that every breath of air, every drop of water, every calorie of food would have to be manufactured, recycled, or imported. And this level of dependence creates a fragile system where a single failure could be catastrophic. And this brings us to a crucial misunderstanding about Mars colonization, because colonization is not simply about reaching a planet, planting a flag, and surviving for a few years. Colonization means creating a stable, growing population that can sustain itself without constant support from Earth. And when we examine Mars honestly, we see that it fails this test in almost every category. Not because humans lack courage or ingenuity, but because the planet itself is fundamentally inhospitable. And this is not a pessimistic view, but a scientific one. Because physics does not negotiate, biology does not compromise, and planets do not adapt to our desires. And this is why Mars, despite our fascination with it, will never be our second Earth, not in our lifetimes, and perhaps not ever. And understanding this does not diminish the value of Mars exploration, but rather
clarifies its true purpose, because Mars is not our escape. Mars is our classroom, a place where we learn about planetary evolution, about the limits of human biology, and about the fragility of life itself. And as we continue this journey, we must set aside fantasy and confront reality, because only by understanding why Mars resists us can we truly understand what makes Earth so precious and why protecting our home planet is not optional, but essential. When people imagine living on Mars, they often picture a red desert under a blue sky, with humans walking freely in advanced suits, building cities that slowly grow into thriving settlements. But this image is deeply misleading, because Mars is not simply a colder, drier version of Earth. It is a fundamentally different world, whose physical conditions impose severe and constant stress on human life. And one of the most underestimated dangers is radiation, because on Earth we are protected by a thick atmosphere and a powerful magnetic field that together absorb and deflect most cosmic rays and solar particles, whereas on Mars this protection is almost entirely absent, meaning that radiation levels on the Martian surface are many times higher than what humans experience on Earth. And this radiation does not merely cause short-term illness, it damages DNA at a cellular level, increasing the risk of cancer, neurological disorders, and reproductive harm. And over long periods of time, this damage accumulates, making long-term habitation extraordinarily dangerous, especially for children and future generations. And while some propose building underground habitats to shield against radiation, this solution introduces new problems, because living underground for decades would have profound psychological effects, including isolation, sensory deprivation, and social strain. And humans are not evolved to live as subterranean creatures, disconnected from natural cycles of day, night, and open environments. And beyond radiation, Mars presents another invisible threat in the form of its soil, because Martian regolith contains perchlorates, toxic chemical compounds that are harmful to human health, interfere with thyroid function, and contaminate water and food supplies.
And removing or neutralizing these chemicals on a large scale would require complex processing systems that further increase the technological burden of survival. And then there is the issue of food production, because agriculture on Earth depends on a delicate balance of soil microbes, water availability, gravity, and sunlight, and Mars lacks most of these conditions naturally, meaning that food would have to be grown in carefully controlled environments, entirely dependent on artificial systems, and any failure in these systems, whether due to mechanical malfunction, human error, or environmental stress, could threaten the lives of everyone involved. And this leads to a central problem of Mars colonization, which is redundancy. Because on Earth, nature provides redundancy through vast ecosystems, multiple food sources, and resilient climate systems, whereas on Mars, redundancy must be engineered, maintained, and powered continuously. And engineering redundancy at planetary scale is enormously difficult and expensive. And this cost is not merely financial, it is logistical and energetic, because every kilogram of equipment sent to Mars requires immense energy, and once there, it must operate reliably for years without resupply. And while automation and artificial intelligence can help, they cannot eliminate the fundamental vulnerability of a closed artificial environment. And this vulnerability becomes even more critical when we consider reproduction and long-term population growth, because no human has ever been born in low gravity, and we do not know how pregnancy, childbirth, and childhood development would be affected by Mars's gravity, radiation, and environmental constraints. And the possibility that humans could suffer severe developmental problems in such conditions cannot be ignored. And without healthy reproduction, a colony cannot sustain itself, no matter how advanced its technology. And this raises ethical questions that are often overlooked, because experimenting with human reproduction on Mars would involve profound risks, and science must acknowledge these risks honestly, rather than dismiss them in the name of ambition. And yet, despite all of these challenges, Mars remains scientifically invaluable, because Mars preserves a record of planetary evolution that Earth has largely erased through tectonic activity and erosion. And by studying Mars, we gain insight into how planets lose their atmospheres, how magnetic fields collapse, and how once habitable worlds become barren. And this knowledge is not academic. It directly informs our understanding of Earth's future, because climate change, atmospheric loss, and magnetic field variations are not theoretical concerns. They are measurable processes. And Mars serves as a warning written in stone and dust, showing us what can happen when a planet loses its protective systems. And in this sense, Mars is not humanity's refuge, but its mirror, reflecting both our hopes and our limitations. And as we continue exploring Mars, we must do so with humility, recognizing that exploration does not imply ownership, and curiosity does not guarantee survival, and the laws of physics will not bend simply because we wish to expand beyond Earth. And understanding this reality is not defeatist, it is empowering, because only by confronting the true nature of Mars can we make informed decisions about the future of space exploration, decisions grounded in science rather than fantasy. Another popular belief surrounding Mars is that advanced technology will eventually solve all of its problems, that with enough innovation we can simply engineer our way past radiation, low gravity, thin atmosphere, and extreme cold. But this belief misunderstands the difference between solving isolated problems and overcoming fundamental planetary constraints. Because technology can mitigate certain dangers temporarily, but it cannot rewrite the basic laws of physics that define a planet. And Mars is constrained by its mass, its distance from the Sun, and its geological history. And these factors determine everything from its gravity to its ability to retain an atmosphere. And no technology currently imaginable can give Mars a magnetic field comparable to Earth's, because Earth's magnetic field is generated by the motion of molten iron in its core, driven by heat and pressure that Mars simply does not possess. And without this magnetic shield, any atmosphere we attempt to create through terraforming would be slowly stripped away by solar wind, just as Mars's original atmosphere was billions of years ago. And this brings us to the idea of terraforming, a concept that has captured the imagination of scientists and science fiction writers alike. And terraforming Mars would involve warming the planet, thickening its atmosphere, introducing water, and eventually creating conditions suitable for life. But when examined closely, terraforming Mars is not merely difficult, it borders on impractical within any meaningful human timeframe. Because even if we could release all of the carbon dioxide trapped in Mars's soil and polar ice caps, studies suggest that it would still not produce an atmosphere dense enough to support Earth-like conditions. And even if we somehow imported vast quantities of gases from elsewhere in the solar system, the absence of a magnetic field would cause that atmosphere to erode over time, meaning that terraforming would require continuous maintenance on a planetary scale, an endeavor that would demand energy resources far beyond what humanity currently controls. And then there is temperature, because Mars receives less sunlight than Earth.
And warming it sufficiently would require either massive orbital mirrors, artificial greenhouse effects, or technologies that remain speculative. And even if warming were achieved, the planet's low gravity would still allow atmospheric gases to escape more easily than on Earth, creating a persistent problem that cannot be easily solved. And when we consider timescales, the reality becomes even clearer, because meaningful terraforming would take hundreds or thousands of years, far longer than the lifespan of individuals, governments, or even civilizations. And during this time, humans living on Mars would remain dependent on artificial habitats, exposed to risks that compound over generations. And this raises a critical question about why we want to terraform Mars in the first place. Because if the goal is to ensure the survival of humanity, then focusing on Mars may be a misallocation of resources, as Earth already possesses everything needed to support life. And preserving and restoring Earth's ecosystems is vastly more efficient than attempting to recreate them on a hostile planet. And this is not an argument against exploration, but an argument against escapism, because the idea that we can abandon Earth and start over on Mars is not supported by science. And in fact, it may distract us from addressing the challenges we face at home, such as climate change, biodiversity loss, and resource depletion. And Mars, in this sense, becomes a symbol of both our ambition and our denial, because it tempts us with the illusion of a clean slate, when in reality there is no substitute for the planet that shaped us. And yet, Mars exploration remains invaluable for another reason, because it forces us to confront the limits of human biology. And these limits suggest that the future of space exploration may not belong primarily to humans, but to machines, because robots do not require air, water, or protection from radiation in the same way humans do. And robotic explorers can operate continuously in environments that would quickly incapacitate human beings. And with advances in artificial intelligence, these machines can make decisions, adapt to unexpected conditions, and conduct complex scientific experiments autonomously.
And when combined with human oversight from Earth or from orbital stations, robots can extend our reach across the solar system without exposing human bodies to unnecessary risk. And this hybrid approach, where humans design, direct, and interpret, while machines explore and endure, may represent the most realistic path forward, not just for Mars, but for deep space exploration as a whole. And recognizing this does not diminish the human spirit, but rather reflects an evolution in how we explore, because exploration has always adapted to the realities of the environment, and Mars is teaching us that the universe is not obligated to accommodate our biology, and that intelligence, not physical presence, may be the key to expanding our understanding of the cosmos. And as we absorb this lesson, Mars shifts from being a promised land to being a proving ground, a place where we test our technologies, our assumptions, and our understanding of what it truly means to be a spacefaring species.
There is also a powerful psychological dimension to the idea of living on Mars that is often overlooked, because humans are not only biological organisms, but deeply social and emotional beings, shaped by millions of years of evolution on a planet rich with sensory input, open landscapes, natural sounds, and complex ecosystems. And when we imagine life on Mars, we imagine survival in sealed habitats, confined spaces, and highly regulated environments where every aspect of daily life is controlled by machines. And while humans can endure such conditions for limited periods, as we have seen in space stations and isolated research bases on Earth, extending this lifestyle indefinitely introduces serious psychological risks, including chronic stress, depression, interpersonal conflict, and cognitive decline. And these risks are amplified by the extreme isolation of Mars, because communication delays between Earth and Mars can range from several minutes to over 20 minutes one way, eliminating real-time conversation and creating a profound sense of disconnection from humanity as a whole. And this isolation would not be temporary. It would be a permanent feature of life on Mars, shaping every relationship, every decision, and every crisis. And when problems arise, as they inevitably will in any complex system, help from Earth would be weeks or months away if it could arrive at all. And this reality transforms Mars colonization from an engineering challenge into a psychological experiment of unprecedented scale. And no amount of training can fully prepare individuals for the cumulative effects of such isolation over decades. And this is particularly concerning when we consider children, because growing up without open skies, natural weather, oceans, forests, or the full spectrum of human society could have unknown developmental consequences. And we must ask ourselves whether it is ethical to subject future generations to such conditions in the name of exploration or survival. And ethics cannot be separated from science, because scientific capability does not automatically justify action. And history has shown us that technological power without ethical reflection often leads to unintended harm. And Mars forces us to confront this reality directly, because the planet does not simply test our machines, it tests our values. And this brings us to the economic dimension of Mars colonization, because sustaining human life on Mars would require a continuous flow of resources, energy, and expertise. And even with optimistic projections of reduced launch costs, the scale of investment required would be immense, and resources devoted to maintaining a small population on Mars could instead be used to improve life for billions of people on Earth. And while this does not mean that space exploration should be abandoned, it does mean that priorities must be carefully balanced, because survival strategies that benefit only a tiny fraction of humanity do not address the broader challenges we face as a species. And this is why the narrative of Mars as a lifeboat for humanity is misleading, because lifeboats are designed to save many lives in an emergency, not to sustain a privileged few while the rest are left behind.
and science must be honest about these implications because misleading narratives can distort public understanding and policy decisions. And yet, despite these concerns, Mars continues to captivate our imagination. And this fascination is not irrational, because Mars represents both our nearest planetary neighbor with a history of water and our first real opportunity to study another world in depth. And exploring Mars allows us to answer fundamental questions about life in the universe, such as whether life ever arose elsewhere, whether biology is a rare accident or a common outcome of planetary evolution, and whether life can persist under conditions very different from those on Earth. And these questions are among the most profound in science because they touch on our place in the cosmos. And robotic missions, orbiters,
Rovers and eventually sample return missions can address these questions far more efficiently and safely than large-scale human settlements. And by focusing on exploration rather than colonization, we align our ambitions with reality, using Mars as a laboratory rather than a refuge. And in doing so, we gain knowledge that can help us protect Earth, develop sustainable technologies, and understand the long-term fate of planets. And this shift in perspective does not diminish the dream of space exploration, it refines it, replacing fantasy with insight. And as we continue to study Mars, we must remember that the universe is not obligated to provide us with another home, and that the rarity of Earth may be precisely what makes life so precious. And recognizing this truth does not weaken humanity's future, it strengthens it, because a species that understands its limits is better equipped to survive than one that ignores them. And Mars, in all its beauty and hostility, teaches us this lesson with remarkable clarity. Another aspect that must be addressed honestly is the popular comparison between Mars colonization and past human migrations on Earth, because it is often said that humans have always expanded into harsh environments, crossing oceans, deserts, and polar regions, and therefore Mars is simply the next frontier. But this analogy fails when examined closely, because every environment humans have ever colonized on Earth still shared the same fundamental biological conditions: breathable air, liquid water, protective atmosphere, and Earth's gravity. And even the harshest environments on our planet provided ecosystems that humans could adapt to over time, whereas Mars provides none of these conditions naturally, meaning that humans would not be adapting to Mars itself, but rather surviving inside fragile technological bubbles completely isolated from the planet. And this distinction is crucial, because adaptation implies a long-term relationship between biology and environment, while survival inside sealed habitats implies constant dependence on machines. And history shows us that complex technological systems are vulnerable to failure, especially over long periods of time. And when such systems fail on Earth, rescue and repair are usually possible. But on Mars, failure could be fatal. And this vulnerability raises fundamental questions about resilience, because a resilient civilization is one that can absorb shocks, adapt to change, and recover from failure. And Mars colonies, by their very nature, would be brittle systems, where redundancy must be engineered at enormous cost, and where even small errors could cascade into catastrophic outcomes. And this reality contrasts sharply with the idea of Mars as a safe haven, because a true refuge should reduce risk, not amplify it. And this leads us to consider the long-term vision of humanity in space, because if planets like Mars are not suitable for large-scale human settlement, then where does our future lie beyond Earth? And one possibility suggested by physics is that the future of human presence in space may not be on planetary surfaces at all, but rather in artificial environments such as space habitats, orbiting stations, or rotating structures that can simulate Earth-like gravity, atmosphere, and radiation shielding. And these habitats could be placed in stable orbits, supplied with solar energy, and designed to be expandable, repairable, and adaptable. And unlike Mars, they would not be constrained by a planet's gravity, atmosphere, or geological history. And this perspective shifts the narrative of space exploration from conquering hostile worlds to building controlled environments where human biology can thrive. And while such habitats are still technologically challenging, they align more closely with the realities of physics and biology. And this perspective reframes Mars not as our future home, but as a stepping stone, a place to test technologies, study planetary processes, and refine our understanding of life beyond Earth. And this distinction offers a more realistic and sustainable path for space exploration, one that values knowledge over conquest and acknowledges the impracticability of transforming Mars into a second Earth.
Matters matters because it influences how we allocate resources, design missions, and communicate goals to the public. And science communication carries responsibility, because exaggerated claims about Mars colonization can create unrealistic expectations and distract from achievable, meaningful progress. And it is important to inspire curiosity without promoting illusion, because the true wonder of the universe lies not in wishful thinking, but in understanding the elegant, often unforgiving laws that govern reality. And Mars exemplifies this lesson beautifully, because it appears familiar enough to spark hope, yet different enough to demand humility. And as we continue to explore Mars, we should do so with clear eyes and open minds, recognizing that exploration does not require permanent settlement, and that understanding another world can be just as transformative as inhabiting it. And ultimately, the question of whether Mars can become a second Earth is not just a scientific question, but a philosophical one, because it forces us to confront how we view progress, survival, and responsibility, and whether we seek to escape the consequences of our actions or to learn from them. And Mars teaches us that there are no easy exits in the universe, only challenges that must be met with knowledge, cooperation, and respect for the limits imposed by nature. And in recognizing these limits, we do not diminish our future, but rather ground it in reality, ensuring that our journey into space is guided not by fantasy, but by wisdom. And that wisdom may ultimately be the most important technology we carry with us as we reach for the stars. As we consider the role of Mars in humanity's future, it is also important to examine the broader context of our solar system, because Mars is not isolated, and any attempt to colonize it must contend with not just its own conditions, but also the limitations imposed by interplanetary travel. And reaching Mars requires months of exposure to microgravity, cosmic radiation, and confinement within spacecraft that are themselves vulnerable to mechanical failure. And these voyages are not trivial, because transporting humans safely to another planet involves not only propulsion and navigation, but also life support systems capable of sustaining crew health, psychological stability, and mission objectives over extended durations. And even with optimal planning, accidents and contingencies must be anticipated. And the reality is that every mission to Mars carries far greater risk than any prior human spaceflight. Because unlike the Moon, where rescue is possible within days, Mars is separated from Earth by tens of millions of kilometers, and delays in communication and resupply are inevitable.
meaning that Martian explorers must be autonomous, self-reliant, and capable of handling emergencies without immediate support. And this requirement amplifies the fragility of any human presence there, because we are accustomed to a planet that is forgiving, full of resources, and embedded within a biosphere that sustains us. And Mars is none of these things, offering instead a landscape that is beautiful, alien, and lethal, where every decision has profound consequences. And this understanding forces a re-evaluation of our ambitions, because the dream of living on Mars cannot be separated from the technical, biological, and logistical realities that define it. And to succeed, we must accept that humans cannot adapt to Mars in the same way they have adapted to Earth's environments, and that technology must compensate for every deficit, from air to water, from gravity to nutrition, from radiation shielding to psychological support. And this compensation comes at enormous cost, not only financial, but also energetic and societal, because sustaining life on Mars requires constant attention, maintenance, and innovation. And unlike exploration on Earth, where failure often results in local consequences, Mars can result in total loss. And this risk is compounded over generations because a permanent
Settlement must reproduce, maintain genetic diversity, and provide adequate living conditions for children. And yet we have no empirical data on human reproduction and development under Martian gravity, radiation, and environmental stressors, making it a domain of profound uncertainty. And uncertainty in this context is not a minor inconvenience, it is a central limitation, because biology does not yield to ambition, and the laws of physics do not bend for imagination. And when combined with social, psychological, and technological factors, the challenge of Mars colonization becomes almost Sisyphean, a task that requires endless effort for minimal guarantee of success. And yet, humans are curious by nature, and we are drawn to challenges that test our limits, which is why Mars remains a focus of exploration, not as a vital replacement for Earth, but as a proving ground for technology, a laboratory for science, and a stage on which we confront our own limitations. And in this sense, Mars is a teacher, not a home, because it teaches lessons about resilience, innovation, and the constraints imposed by nature. And these lessons extend beyond planetary science into philosophy, ethics, and long-term planning, because understanding what humans can and cannot do is essential for making rational choices about our future. And when we approach Mars with humility, acknowledging the impossibility of creating a second Earth, we free ourselves from illusion and embrace the true potential of our species, which is not merely to survive on another planet, but to understand, to innovate, and to expand the reach of knowledge. And by doing so, we can achieve something even more remarkable than settlement, which is mastery of the challenges posed by extreme environments, mastery of the interface between human biology and technology, and mastery of the wisdom required to navigate a universe that is indifferent to our desires. And Mars, in all its hostility and beauty, exemplifies this challenge, because it offers no shortcuts, no easy solutions, and no guarantees. Yet it rewards preparation, intelligence, and perseverance with knowledge, insight, and perspective. And these rewards are far more enduring than the ephemeral glory of planting a flag, because they teach us not only about another world, but about our own, about the preciousness of Earth, the limitations of our biology, and the responsibilities that come with the power to explore. And in this recognition lies the true promise of Mars exploration, a promise grounded in reality, guided by science, and illuminated by the human mind, which, when applied wisely, can overcome obstacles that biology alone cannot. And through this understanding, we discover that while Mars may never be our second Earth, it can still expand our understanding, challenge our ingenuity, and inspire the next generation of explorers, engineers, scientists, and dreamers to reach farther, think deeper, and act more wisely. And this is the ultimate lesson that Mars imparts, not as a destination, but as a teacher. And it is a lesson that every human, now and in the future, must hear, understand, and respect.
In addition to the physical, biological, and psychological challenges, there is also a critical economic and political dimension to Mars colonization. Because building and maintaining a human presence on Mars is not only a technological challenge, but a global enterprise that requires unprecedented cooperation, funding, and long-term planning. And when we consider the costs, the scale becomes almost unimaginable. Because launching materials, equipment, and humans to Mars consumes enormous amounts of energy, financial resources, and engineering precision. And even with projected reductions in launch costs through reusable rockets or advanced propulsion, the sheer scale of sustaining a colony, providing food, water, air, shelter, and medical care would require continuous investment for decades or centuries. And these resources are finite, meaning that prioritization becomes essential, because investing trillions in a small, high-risk settlement may not yield the proportional benefit compared to investing in Earth's sustainability, space infrastructure, or robotic exploration. And this raises profound questions about what our goals truly are in exploring Mars. Because if the purpose is survival, education, or knowledge, then smaller robotic missions can accomplish much more efficiently than humans living on the surface. But if the purpose is prestige, adventure, or fulfilling a narrative dream, then human settlement may serve more as a symbolic gesture than a practical solution. And symbolism alone is not sufficient when dealing with environments that are literally life-threatening. And in this context, we must examine the role of private ventures, such as those led by visionary entrepreneurs who dream of Mars colonies. Because while private innovation can accelerate technology, it cannot change fundamental physics, biology, or planetary conditions. And no amount of investment can reduce radiation, increase gravity, or create a breathable atmosphere without massive engineering and energy input. And even ambitious plans must contend with the realities of orbital mechanics, communication delays, and the necessity of maintaining life support systems continuously, because Mars does not forgive mistakes. And the scale of required logistics, redundancies, and fail-safes is enormous, far beyond anything humans have attempted before. And this is why the idea of self-sufficient Martian cities is currently aspirational rather than achievable. Because sustaining even a few hundred people indefinitely would require continuous supply from Earth, a fragile dependency that undermines the notion of true colonization. And when we consider these limitations, we also see why Mars has become a mirror for human ambition. A canvas upon which we project our desires for expansion, conquest, and survival. Yet it is a mirror that reflects our biological fragility, our technological limitations, and the ethical dilemmas inherent in sending humans into extreme environments. Because while humans have always been explorers, survival in space is not the same as survival on Earth. And as such, Mars challenges our assumptions about what it means to explore, what it means to settle, and what it means to thrive. And by studying Mars realistically, we gain insight not only into planetary science, but also into ourselves. Because confronting the harsh realities of another world teaches us humility, patience, and prudence. And it also emphasizes the value of our home planet. Because Earth is a rare convergence of conditions that allow complex life to flourish. And the scarcity of such environments underscores the importance of stewardship.
And as we project ourselves towards Mars, we should ask, are we seeking to escape our responsibilities or to extend our understanding? And in this framing, Mars serves less as a replacement for Earth than as a laboratory for testing ideas, refining technologies, and preparing humanity for environments that are far less forgiving than the one we evolved in.
Mars is not a failure of imagination, but a triumph of realism, because it forces us to distinguish between what is possible, what is desirable, and what is ethical. And in doing so, we refine our ambitions, focus our resources, and orient our species towards strategies that maximize knowledge, survival, and sustainability. And this approach ultimately aligns with the best of human exploration, which is guided by curiosity, disciplined by science, and informed by the recognition that the universe does not bend to wishful thinking. And by embracing this philosophy, we can pursue the dream of space with open eyes, respecting limits, celebrating discovery, and understanding that the greatest achievement may not be setting foot on another world, but learning how to live wisely, responsibly, and intelligently in the only home we truly understand, which is Earth, while preparing ourselves to interact with worlds like Mars, not as settlers seeking to replace our planet, but as explorers seeking to comprehend, experiment, and adapt our knowledge. And in this perspective, Mars remains a vital part of our journey into the cosmos, not as a second Earth, but as a teacher, a challenge, and a testament to the ingenuity and perseverance of the human mind. As we continue to examine the realities of Mars, it is important to consider the technological trajectory required to even attempt long-term human presence, because reaching Mars is only the first step, and surviving there indefinitely requires a combination of life support, energy management, habitat construction, and environmental monitoring at a level of sophistication that is unprecedented. And each of these systems must operate flawlessly for years, because unlike Earth, where nature provides redundancy and repair mechanisms, Mars provides none, and any failure could have immediate and fatal consequences. And this requirement for flawless systems extends to food production, because humans cannot rely on foraging, hunting, or natural agriculture. And growing crops in Martian soil is not feasible without extensive chemical processing, hydroponics, or synthetic alternatives. And each of these introduces new dependencies and potential points of failure. And then there is the question of water, because while Mars has ice, extracting it, purifying it, and distributing it safely is an enormous engineering challenge that consumes energy and resources. And even if these systems are established, they must be maintained continuously, because any interruption could compromise life support. And this is a stark reminder that Mars is fundamentally a hostile world, one that does not naturally support the biological processes we take for granted on Earth. And beyond the immediate survival challenges, there is also the issue of long-term adaptation, because humans evolved over millions of years in Earth's gravity, atmosphere, and magnetic field, and our biology is intricately linked to these conditions, and placing humans in low-gravity, high-radiation environments for extended periods alters physiology in ways that are not fully understood, from weakening bones and muscles to altering cardiovascular and neural systems. And these effects are compounded across generations, raising questions about reproduction, growth, and genetic stability. And while some advocate for genetic engineering or pharmacological intervention, these approaches carry ethical, medical, and technical uncertainties that cannot be ignored. And when we expand our consideration further, we must also consider the cultural, social, and psychological dimensions, because humans are social beings whose well-being depends on interaction, community, and access to diverse environments. And Mars, with its isolation, confined habitats, and dependence on artificial systems, challenges all of these simultaneously, creating Stressors that are difficult to predict and impossible to eliminate entirely. And this combination of biological fragility, environmental hostility, and technological dependence underscores why Mars will never be a second Earth. Because colonization implies more than temporary presence. It implies sustainability, resilience, and adaptability. And in all these areas, Mars presents fundamental barriers that are unlikely to be overcome in the foreseeable future. And yet, Mars remains an invaluable target for exploration because it provides insight into planetary evolution, the history of water, and the possibility of life beyond Earth. And robotic missions, orbital satellites, and autonomous systems can achieve this exploration safely, efficiently, and repeatedly, gathering data that informs not only planetary science, but also Earth science, astrobiology, and future space engineering. And in this way, Mars becomes less a goal for habitation and more a platform for discovery, a place where knowledge is harvested rather than lives risked. And this perspective reframes our ambition, emphasizing preparation, understanding, and strategic investment rather than romantic notions of migration. And it also aligns with the scientific method, which demands that we confront evidence, accept limitations, and design solutions compatible with reality. And by taking this approach, we ensure that exploration contributes meaningfully to humanity's understanding, while minimizing unnecessary risk. And in the end, the true lesson of Mars is that ambition alone cannot override the laws of nature, that dreams must be tempered by science, and that the most remarkable achievements come from aligning human ingenuity with the constraints of the universe. And in this alignment lies the path forward, where we can expand our reach, extend our knowledge, and explore the cosmos intelligently, responsibly, and sustainably. And recognizing that Mars will never be our second Earth is not a limitation, but a guidepost, a truth that allows us to pursue space exploration with clarity, purpose, and wisdom, understanding that survival, adaptation, and discovery require both courage and humility, and that the universe rewards those who respect its laws as much as those who dare to explore it. And in this way, Mars teaches us the greatest lesson of all, that knowledge, preparation, and respect for reality are the true measures of human progress, and that while we may never walk freely on the Martian surface as we do on Earth, we can still expand our understanding, our technology, and our imagination, creating a future where humanity thrives not by escaping our home, but by understanding it and the universe beyond it.
Furthermore, when considering Mars, we must also reflect on the broader implications for humanity as a species, because the dream of colonization often carries with it implicit assumptions about expansion, survival, and legacy. And yet Mars challenges these assumptions at every level, because it is not merely an extension of Earth, but a fundamentally alien world whose physical, chemical, and environmental realities impose limitations that no human ingenuity can fully overcome. And recognizing this forces a redefinition of what exploration means, because exploration does not require settlement, and understanding does not require presence. And the success of a mission should not be measured by footprints left on a planetary surface, but by the knowledge gained, the technologies developed, and the lessons learned. And in this light, Mars becomes a proving ground, a laboratory, and a teacher rather than a home, because it allows us to test life support systems, study planetary history, and prepare for environments beyond Earth without exposing humans to unnecessary risk.
And this perspective also has ethical implications, because sending humans to a hostile planet for the sake of prestige, adventure, or speculation imposes profound risks on individuals who may not fully understand the long-term consequences. And as scientists and explorers, we have a responsibility to weigh ambition against reality, desire against evidence, and dreams against the immutable laws of nature. And when we do so honestly, the conclusion is clear. Mars will never be our second Earth, not in the sense of a self-sustaining, thriving civilization that mirrors the conditions of our home planet. And yet, this conclusion does not diminish the value of Mars exploration, because exploration guided by science, prudence, and curiosity yields profound rewards. And those rewards are intellectual, technological, and philosophical. Because by studying Mars, we learn not only about another world, but also about the fragility of life, the rarity of habitable planets, and the preciousness of the conditions that allow humans to exist. And this knowledge informs our decisions on Earth, guiding efforts in sustainability, environmental stewardship, and planetary defense. And beyond practical science, Mars exploration inspires a deeper understanding of our place in the cosmos, because it reminds us that we are small, temporary, and contingent beings navigating a universe that is indifferent to our desires. And yet, within this universe, the human mind has the capacity to understand, to imagine, and to innovate. And these capacities are the true markers of our progress. And when applied wisely, they allow us to extend our reach into space, not by abandoning Earth, but by complementing it, by creating technologies, systems, and knowledge that enhance survival, resilience, and comprehension. And in this context, Mars becomes a symbol, not of escape, but of aspiration, a challenge that tests human intelligence, endurance, and ingenuity. And it teaches us to respect limits, understand complexity, and act with foresight. Because the universe does not bend to wishful thinking, and the laws of physics, chemistry, and biology do not yield to ambition alone. And by embracing this reality, we gain a framework for sustainable exploration, where knowledge, preparation, and respect for nature are prioritized over romance or fantasy. And this approach ensures that humanity's efforts in space are meaningful, efficient, and responsible. And it allows us to extract the maximum value from each mission, rover, or satellite. Because every experiment conducted, every measurement taken, and every sample returned informs not only our understanding of Mars, but also of Earth, the solar system, and the principles that govern planets, atmospheres, and life itself. And in this way, Mars exploration becomes both a scientific endeavor and a philosophical one.
Because it teaches us humility, patience, and foresight, and it challenges our assumptions about survival, adaptation, and the scope of human ambition. And ultimately, the most profound lesson of Mars is that survival is not guaranteed by travel, settlement, or ambition, but by understanding, innovation, and the wise application of knowledge. And this is the message that I, as a physicist, a professor, and a student of the universe, wish to convey. Because it is only by accepting these truths that humanity can pursue exploration responsibly, achieve meaningful progress, and prepare for a future in which knowledge, creativity, and prudence, rather than escape, define our legacy among the stars. Finally, as we conclude this exploration of Mars, it is essential to reflect on what the planet truly represents. Because Mars is often depicted as humanity's backup plan, a lifeboat in the cosmic ocean. Yet this narrative oversimplifies the profound complexities involved. And when we examine Mars with the lens of physics, biology, and planetary science, we see that it is not a refuge, but a challenge, a world whose environment demands constant adaptation, technological ingenuity, and deep understanding. And every aspect of survival on Mars, from radiation shielding to life support, from water extraction to food production, from psychological well-being to long-term reproductive health, requires solutions that are currently beyond our full capability. And this is not a limitation of ambition, courage, or ingenuity, but a reflection of the reality that Mars is fundamentally different from Earth. And attempting to inhabit it without acknowledging these differences would be reckless and ethically questionable. And yet, Mars remains invaluable as a target for exploration because it provides a unique laboratory to study planetary evolution, the potential for life beyond Earth, and the long-term fate of planets. And by studying it, we gain insight into our own world, the fragility of life, and the conditions that make Earth uniquely habitable. And these lessons extend far beyond science into philosophy, ethics, and the way humanity approaches its future, because they teach us humility, foresight, and respect for the forces of nature. And they remind us that true exploration is not measured by footprints left on another world, but by the depth of understanding gained, the technological progress achieved, and the wisdom acquired. And when we approach Mars in this way, not as a second Earth, but as a teacher and proving ground, we align our ambitions with reality and ensure that our endeavors contribute meaningfully to knowledge, survival, and the long-term advancement of humanity. And we also learn that space exploration is not an escape from responsibility, but an extension of it, because the universe rewards preparation, understanding, and respect, and punishes hubris, neglect, and wishful thinking. And these principles apply equally to Mars and to Earth, where the challenges of climate change, resource management, and sustainable civilization demand the same combination of knowledge, innovation, and prudence. And by taking these lessons from Mars seriously,
because it teaches us humility, patience, and foresight, and it challenges our assumptions about survival, adaptation, and the scope of human ambition. And ultimately, the most profound lesson of Mars is that survival is not guaranteed by travel, settlement, or ambition, but by understanding, innovation, and the wise application of knowledge. And this is the message that I, as a physicist, a professor, and a student of the universe, wish to convey, because it is only by accepting these truths that humanity can pursue exploration responsibly, achieve meaningful progress, and prepare for a future in which knowledge, creativity, and prudence, rather than escape, define our legacy among the stars. So, everyone, that brings us to the end. I hope you've gained a deeper understanding from what I explained today. Let me know in the comments what kind of topics you'd like me to explore next, and subscribe to the channel so we can continue this journey of knowledge together. Because when we understand more, the world moves forward.